and welcome to Space2090, the Space Exploration Podcast. This podcast is for everyone enrolled in Geography 2090, Space Exploration, in the Department of Geography at Western University. My name is Danny Bednar. I'm a part-time assistant professor in the Department of Geography at Western University in London, Ontario, Canada, as well as an analyst with the Canadian Space Agency in Ottawa, Ontario. This week we're continuing our discussion of the Red Planet, this time focusing a bit more on the engineering of Mars exploration via discussion with Western alumni Dr. Raymond Francis. Raymond is the lead system engineer for the Aegis Autonomous Science System for the ChemCam instrument on NASA's Mars rover. That would be the Curiosity rover, the one that is currently active. He is also the science payload uplink lead for the same ChemCam instrument on Curiosity. For the upcoming Mars 2020 mission, Raymond is currently the science team training coordinator for the project science officer and will be a member of the science team for that rover as well. So I chatted with Raymond last week, and like the other podcasts this week, was still battling some fatigue from the conference and travel, but overall I think we covered off the notion of roving Mars quite well, especially the Mars 2020 upcoming rover mission, as well as its instrument suite. So with that, I hope you enjoyed the conversation, and as always, make sure to take good notes. All right, 2090. For this week's podcast, I'm here with a friend of mine, Dr. Raymond Francis from the Jet Propulsion Laboratory in the United States, of course, an affiliate laboratory of NASA. Thank you for being here, Raymond.
My pleasure.
So, first of all, did you know that when you Google Raymond Francis, you do not come up, a health expert doctor comes up?
Yeah, and he's the kind of guy who writes kind of kooky books about how to get healthy naturally.
Yeah. I saw something. I didn't think you were purveying magnets to cure my illnesses.
No, I'm not.
If they Google Raymond Francis, you are not the one selling alternative health books.
That's right. I'm not. That's somebody else.
If
they Google Raymond Francis JPL, they'll find me.
That is exactly what I did, thankfully, to look up your bio. So the students in this course have been learning about kind of the advancement of exploration, at least in the last couple of weeks, from things like flybys to orbiters to landers, and eventually surface operations and surface movement, which comes in the shape of rovers. So from your background and your experience, what have rovers really contributed specifically to Martian science?
So there's only so much you can tell from orbit. You can get a global view from orbit. You can see the whole planet, but you can only see it to a certain resolution. If you're looking with cameras, there's a limit to how fine a scale you can see on the surface. And if you're looking with spectrometers, some of them can see the surface fairly well in certain wavelengths, but the atmosphere may or may not block it, or even the dust might block it. Mars is covered almost everywhere with a thin layer of dust, and so sometimes when you look from orbit, your spectrometer that tells you the composition of things is just telling you the composition of the dust. So if you really want to understand what the planet is like, you need to go down to the surface, and landers can be very useful, but of course they really only let you look at one small place. Rovers let you move around, place instruments right up against a rock that you might choose, or go to a new place, compare how the chemistry of the rocks changes as you climb up through a stratigraphic section or as you cross over some large distance. And so that mobility allows us to see things up close and also see things over some area.
Yeah, and if I remember properly from my days in the analog mission control, there's kind of a big distinction between the science we can do remotely and remote observation and so to speak contact science. Is that right?
Yeah, on a mission like Mars Science Laboratory, we tend to progress from what we call remote sensing instruments to contact science, where you have to choose only a small number of places to actually place an instrument right up against a target and view it from very close millimeters or even directly in contact range. And then you can go even further and you can take samples and measure them inside the rover, where we have a miniaturized laboratory. And so we have this progression from remote science to contact science to sampling.
Yeah, and we'll definitely talk about that a little more. I just want to bring the students along a little bit through the history of Mars rovers. There's been a few, of course, and we'll kind of skip over the first one, Sojourner, which was a little one, and I do talk about briefly in the other podcast for this week with Dr. Tanya Harrison. But really, the first long duration and exceptionally long duration rover missions were the Mars exploration rovers Spirit and Opportunity. Both of them have now completed operations, but from a science and engineering perspective, if you want to separate the two or not, what was really the legacy of these essentially marathon missions?
Yeah, so the MER rovers, as we call them, Mars exploration rovers, they were designed with the intent of lasting for about 90 days each on the surface. And kind of unexpectedly, they kept going. They were solar-powered vehicles, and we expected that dust, that ubiquitous Martian dust, settling on the solar panels would bring an inevitable end to the mission. But that happened more slowly than we expected, and we had some happy circumstances of wind actually cleaning some of the dust off the panels. And so the rovers were able to continue for a long time. One of them as long as 15 years. So that allowed a much broader range of scientific investigations to happen over that time, over a larger geographic area, and just a long time, a large number of observations. Both of them, these two rovers in different places on opposite sides of the planet. And so we got a lot more depth and breadth of measurements than we would have otherwise. Overall, those missions were part of a strategy that NASA had at the time to follow the water on Mars. If we wanted to understand the history of Mars and if it had ever been inhabited by life of any kind, we thought that going where there might be signs of water was a good first step. And both of them found evidence, strong evidence in many different domains for past water, showing the physical features of water eroding rocks and shaping things, but also more importantly, geochemistry that proved that the rocks were forming when the planet was still wet. And so we learned a lot about the ancient history of that planet, and it really helped us to solidify an image of a planet that is dry and dusty today, but that was warm and wet at some time in the past. And that warm, wet Mars is a place that you can imagine life having perhaps taken root. MER wasn't able to really answer that question, but it was able to show us what ancient Mars looked like in quite a bit of detail.
Yeah, and it's set up, of course, I mean, a mission that followed up and a mission that you've been involved with for the last little while. And this is no coincidence, of course, long duration exploration programs tend to follow one another, sometimes not in a perfect alignment, but certainly the design and the questions for the follow-up rover, the Mars Science Laboratory, or what we know as Curiosity, were heavily influenced by what the MERS had found early on in the missions.
Yeah, that's absolutely the case. MSL, Mars Science Lab, was designed to be a follow-on and to build on the technical and scientific successes of those earlier missions.
So, thankfully MSL is still going today. Of course, now you're especially yourself, and I assume many people in the teams around you are having to balance an actively operating rover and a future mission that we'll talk about that's going to follow up. Hopefully we have many more years of MSL ahead of us, but when we look back at some of MSL's major achievements or findings on the surface, what do you think those might be 10, 20, 30 years from now?
So I think MSL has, followed on from MER, which showed that the planet was wet even when it was still geologically active. And at our Gale crater landing site, which is sort of equatorial, it's a large crater about 150 kilometers across, about 5 kilometers deep. And we were able to show that this place was wet too, that in fact there was a lake here that lasted for quite an amount of time. It was like a persistent lake that was putting down sediments over a long period. But even more, what MSL was able to show is that this environment was habitable, that we had a lake with creeks flowing into it, we had sediments moving around, the kind of lake bottom sediments that bacteria can readily live in, or things like algae could live. And also that this water was at a clement temperature. We can't say precisely what it was, but you can imagine it was above freezing and not so hot as to be difficult for life. And that the chemistry of that water was of a sort of neutral pH, that it had nutrients dissolved in it that might have been useful to microbes. So we have the first clear, solid evidence for a habitable environment in ancient Mars, which is something that we didn't have before. So we know now that Mars was habitable. We don't know if it was inhabited, but we know it was habitable. And even more, we know with some precision when that was, because we were able to do a geochronology experiment with the laboratory on the rover. And so we were able to take those mudstones that were formed in those lake bottom sediments and get an age of about 4 billion years, which is very old, about as old as we had expected. But that means that there was a lake there something like 4 billion years ago that was habitable. And so I think that will be one of the standout results from the MSL mission.
So obviously those discoveries regarding the history and the presence of water and potential climatic conditions for life were heavily influenced by the findings of particular instruments. Are there particular instruments that or any single particular instrument you think has been kind of central in some of these findings?
So I think the important thing about MSL is that the collection of instruments we have were selected as a suite because they work well together. We really have this strategy of starting with imaging. You take pictures and you see what's around the rover. And then you can choose from everything you see, you can choose a few things to get remote chemistry on with the ChemCam instrument. And having done that, you can move in for closer inspection using the instruments on the arm. We have the alpha particle X-ray spectrometer, which allows us to get another assessment of the geochemistry. It looks sort of at bulk geochemistry of the rock, where ChemCam is looking at very fine points. And the MALI camera, which allows us to look up close at the rock and see, for example, whether it's a sandstone with coarse grains or a mudstone with finer ones. But to really answer questions of habitability, you have to use all of those tools to find the right places to drill and take samples to put into the ChemIn and SAM instruments, which together form the internal miniaturized laboratory. And it's with ChemIn and SAM that we finally determine the mineralogy of the rocks and their chemical composition, and whether there are organics and how the rocks are formed in a detailed way. And so you can't answer the questions with SAM, even if you think SAM is what gives you the final answer to some of these questions. You can't get there unless you use the other tools to figure out where to sample. And so it really comes as a suite of instruments, and using them effectively is one of the biggest challenges of operating that mission.
MSL, we don't know how much longer it'll last, but so far, other than the general wear and tear that all rovers experience, it's going okay. But next year, NASA is launching the Mars 2020 rover, which will be a follow-up, very similar chassis to the MSL mission, but a slightly different suite of instruments. In fact, suite of instruments that I'm particularly curious about and interested in talking about. But before we do that, what will be your role, or what is your role right now on the Mars 2020 mission?
So I'm working in a few ways on 2020. First, I'm the science team training system engineer. So we have a new vehicle and a new payload suite and a new mission with different goals and objectives than MSL, and a new science team. And so we need to train the science team to use that system with its payload and its vehicle, which is different than the previous mission. And some of them have not, some of these scientists have not been on previous missions. We need to train that science team to work together to use the flight system, as we call it, the rover and the payload, and work in the operations process that you need to operate a spacecraft to do all of that in that context and effectively use it to explore the landing site on Mars. And so we're running a series of training simulations focusing on how you use those instruments to explore and how you work together as a science team to understand a geological environment. And I'm helping to design and implement those simulations. So that's my main role on 2020 right now. I'm also a member of the SuperCam science team, and my specialty there is in instrument operations and in artificial intelligence to do autonomous instrument targeting, which is a thing that we'll have on the mission. And then finally, I'm also helping out a little bit, just building the systems that will allow us to process the data when it comes back.
Yeah, I'm trying to picture that. So you guys are obviously getting ready for this rover. Obviously, the rover that's going to be launched is right now it's in the clean room, it's being put together. Are you guys working with like a mock rover or a mock set of instruments out in the field?
Yeah, so when we do these training simulations, for the highest fidelity ones that we do with the science team, we don't usually bring a robot, we don't bring a vehicle, because we can simulate the data that they'll see without having that vehicle. So we can bring spectrometers and cameras and robotic instrument mounts and things just to gather the data without having to deal with a lot of heavy and cumbersome robotics. So we'll have a human team which is operating all those instruments and simulating that, but then we put it into the same pipeline of data processing and into the same operations tools that they would use for the real mission. And so for the most part, they can't really tell that it isn't coming from the rover because the data looks about right until they start looking at photographs and seeing blue sky.
Right. Or insects.
Yeah, we do our best to keep those out of the view.
So what about from the engineering side, though? Is there a kind of duplicate rover to get a sense of wheel traction and things like that, and how far the arm can reach and balance and everything along those lines?
Yeah, so we do a lot of partial, what we call test bed or engineering models, and also a full system test bed. So we're actually still building the final vehicle system test bed, like the whole rover model that has everything. But we've already got a copy of the robotic arm, which behaves the same way as the flight arm, copies of the instruments. We have a mobility test vehicle, which doesn't have any of the instrumentation or anything else, but has the same wheels and the same chassis and the same ground pressure. And so you can test all the driving and all of the autonomous navigation over the surface with that. So in all the little pieces, we have ways of simulating all the different parts, and we also have a full system simulator.
Okay, so let's jump into a couple of these instruments because I want the students to understand, if you're building a rover, what do you bring with you? And the obvious answer is obviously a camera, some type of spectrometer, but there's a lot more you can do. There's also different kinds of cameras and spectrometers. I'll just go down the list of the primary ones, not all the sub instruments, but or subsystems. But start with the Mastcam Z. This is really just, from my perspective or from my understanding, I guess, a pretty typical camera on board with some zoom functionality to pretty much tell you guys where the rover is.
Yeah, so I think we do start with the cameras. We have what are called engineering cameras, and that's the set. We have 3 pairs of stereo cameras that allow us to see what's around us, the nav cams, and 2 pairs of has cams that are mounted lower. But next to the nav cams up on the rover's mast are the stereo camera called Mastcam Z. Yeah. Mastcam Z is a science camera primarily, and it's two upgraded versions of the Mastcams that we have on MSL. But the Mastcam Z here for zoomable. So we have the ability to zoom in stereo or in just one left or right eye as we see fit. And that allows us to take very close, high-resolution images of targets that we choose. So usually the nav cams will see everything. The Mastcam will be pointed at things that are interesting. And what's also worth noting is that the Mastcam is also a multispectral camera. So where the engineering cameras give us sort of regular RGB color, the Mastcam Z will give us red, green, blue like that, but also several more filters that are sensitive to particular emissions from particular minerals, chemical elements within the rocks. And we also have a solar filter on there that allows us to take pictures of the sun.
Yeah, so, I mean, that's a good point. The difference between, of course, there's an entire suite of cameras essentially dedicated to looking at the rover itself. And some of those selfies we see are, of course, for public release and because they're cool to see the rover on the surface. But for you guys, and especially for the planning team, those are incredibly valuable, right?
That's right. Yeah. And we deliberately included a camera on the arm again so that we would be able to image most parts of the rover and monitor how they're doing.
So some of the cool kind of relatively new instruments coming along, this Mars Environmental Dynamics Analyzer, MEDA. What is this and how's it gonna work?
So MEDA is the contribution of Spain to this mission. And it is an upgraded version of the REMS instrument on MSL, the Rover Environmental Monitoring Station. So basically, it's the weather station that the rover carries. We measure wind, temperature, relative humidity, absolute humidity, the surface temperature and air temperature, these kinds of things. We also, with MEDA, will have an imager this time. We have a sky cam, which is an all-sky imager and sort of a fishbowl lens, sits on the back of the rover, allows you to see the whole sky in a single image. And that allows us to monitor the dust loading in the atmosphere and also the motion of clouds.
Okay, so I completely forgot there was a similar instrument on MSL, but what there's not really a similar instrument of is the oxygen ISRU experiment. This, if I'm not wrong, is pretty novel.
That's right. Yeah, Moxie is a totally new thing. This will be the first time that we can demonstrate producing oxygen from the carbon dioxide atmosphere in situ on the surface. And this is partly a technology demonstration, but it's also, the idea is that we can prepare for future human exploration of Mars by demonstrating some of the technologies that we would need for that. You're going to want to make oxygen locally if you ever send astronauts.
Yeah, so I remember you telling me about this in the past, how this is going to work, but essentially it's an effort to separate the oxygen elements, the oxygen atoms from whatever kind of ambient material is around the rover, namely CO2.
Yeah, so Moxie will use a chemical process to extract oxygen from the atmosphere of Mars, which is principally carbon dioxide. It'll be in very small amounts. It's just a demonstration, and we aren't going to use it for anything. There's nothing on the rover that needs to breathe oxygen. But it'll allow us to understand how well we can use that in the real environment of Mars with the technical challenges of doing it remotely and the fact that the air is not pure carbon dioxide and it's got dust in it and other things. So this will be a real demonstration of how practical this is.
So I got to say the NASA acronym game is on point for this mission. Moxie was pretty good. Mars Oxygen ISRU experiment, an acronym with an acronym in it, which deserves bonus points. The next one I just want to ask quickly about Pixel. Pretty good as well. Planetary instrument for X-ray lithochemistry. What are we doing with lithochemistry, and how are X-rays helping us get a sense of, well, lithochemistry?
Yeah, so lithochemistry here, meaning the chemistry of rocks, helping us to understand the lithology of these rocks. So Pixel is basically a scanning X-ray fluorescence spectrometer. It allows us to shoot a narrow X-ray beam into a tiny spot on a rock and get back some corresponding radiation from exciting with those X-rays the electrons in the atoms of the rock. We get back corresponding wavelengths of light that tell us what the elemental composition of that rock is. And Pixel is arranged in such a way that you can scan that X-ray beam over the surface of the rock and make a small micro map of the elemental composition at the millimeter scale.
Is Sherlock the best acronym you've ever seen in space?
There's some clever ones out there. People work hard to try and make these things sound clever.
I'm a fan. I think it's well done. But of course, Sherlock is the instrument for scanning habitable environments with Raman, and luminescence for organics and chemicals. It's another spectrometer on board in the UV wavelength. What do we know about what Sherlock's going to be doing?
So Sherlock, like Pixel, is mounted on the end of the robotic arm. It allows us to place that right up against a rock. Sherlock can scan a very fine resolution over a sort of centimeter-sized area on the surface with a Raman spectrometer. It's a type of laser spectroscopy where you excite, again, the atoms in the rock, but here in the UV, as you mentioned, rather than in the X-rays. And your Raman allows you to understand the crystal structure of the rock, which basically means mineralogy. And if there are any organic compounds there, they can also respond to this. And so you're basically getting composition of the rock. What molecules is it made of, basically? Pixels tell us what atoms. Sherlock will tell us more what molecules and what minerals are in this rock.
All right, so we're doing a lot of what we've done in the past, learning what the rocks are essentially made of, their chemical and lithochemistry. But RimFacts is doing something that I love and that Insight is working on right now. Hopefully we'll have increased successes, and that's looking at the subsurface, the structures of the rocks, the structures of the subsurface specifically. Another cool thing about RimFacts is it's going to be operated out of Norway, principal investigator operating outside of the United States, which reflects the international collaboration that these missions often are. I'm excited about any subsurface research in planetary science. What are we hoping to come from the RimFacts data?
Yeah, so RimFacts is a ground penetrating radar system. It's the first time we'll operate something like that on Mars. And it's helpful to be able to understand what's below your feet. You know, the drill will only go down a few centimeters, but you can peer into the deep subsurface and see whether it's all the same material that you see at the top or whether there's a distinct change. You may even be able to trace structures that you see emerging out of the ground somewhere. Like if there's a rocky hill that disappears below the surface, you may be able to trace where it goes underneath. And so it can help you build an idea of the context of the places that you're observing with your cameras.
The last but not least, in terms of instruments, of course, the one you're going to be working on, I suppose, primarily SuperCam. And what is SuperCam?
So SuperCam is the follow-on to the ChemCam instrument on MSL. ChemCam gave us a remote laser-induced breakdown spectrometer, and that is a powerful laser that you focus on a target, usually a rock, and that puts on the order of a megawatt per square millimeter of laser power into the surface, which is enough to turn solid rock into plasma. You vaporize a bit of the rock, and that glowing plasma emits characteristic wavelengths of light that allow you to tell what atoms it's composed of. And so it's a very useful tool for remote spectrometry, because now you can zap several rocks all around the rover in a maybe 5 rocks. You get 150 spectra on 5 different rocks in an hour. And that's much faster than driving up to it and putting the robotic arm. ChemCam also gave us a remote microimager, which is a context camera that looks through the same telescope that focuses the laser and allows you to see exactly where you shot. SuperCam on Mars 2020 will take those capabilities, increase the RMI, the remote microimager capabilities, by making it a color camera now, but we'll also add some more sensor modes. So we'll have a remote Raman spectrometer, similar to what's on Sherlock. We'll also have an infrared spectrometer that we can focus through the telescope. And we'll also carry a microphone. And each of those will give us some information, augmenting what we get from just the LIBS, the laser-induced breakdown spectrometer. And so we have a really versatile set of different remote spectrometer modes that we can use to understand our various rock and soil targets and even the atmosphere.
So first of all, why do you have a microphone on Mars?
So there is an atmosphere, and you can imagine it might be interesting to listen to the wind or understand whatever other kinds of vibrations a microphone can pick up. But of particular interest to SuperCam is that when the LIBS laser is coupling with the rock and vaporizing the surface, it turns rock into a expanding ball of plasma, and you get a little pop with that. You get a little explosion. And if the laser is well focused, you get a different waveform than if the laser is poorly focused. And the degree to which energy is actually being transmitted into the rock couples very closely with the degree to which it makes noise. So it's actually a very useful way of understanding how well the laser is interacting with the rock, and you can get some compositional information out of that simple acoustic physics.
Huh. I had no idea. That sounds interesting. I would have assumed it was purely for meteorological purposes, but there you go. It's actually going to have
Yeah, no, it's actually a directed microphone, so it mostly will pick up the noise from the LIB shots itself, but I'm sure we will find other things to do with it.
So, of course, your role on this and your background and what you worked on in your PhD at Western was adding a layer of autonomy to this. What role will autonomy play, not just in SuperCam, but on the 2020 suite as a whole?
Yeah, so in order to make the mission more productive, we're pulling in new kinds of system and subsystem autonomy. There's plenty of things on board the rover where it's smart enough to manage its own battery and its own various onboard systems so that it can keep things that need to be warm by knowing what their temperature is and do a lot of that automatically. So that's good news. We also have the ability for autonomous navigation. You can give it a destination and it will navigate its way there and keep itself safe. And that will be enhanced from MSL, where we had AutoNav, but this one will allow it to drive faster. We won't have to stop to take pictures anymore. It processes fast enough to drive continuously and save a lot of time that way. On the ground side, we also do a lot of automated sequencing, what we call it. And this is where we take a description of the activities we want the rover to do, a very technical and detailed one, and then automatically produce the sets of commands that we'll send up to the rover, rather than having to hand edit those commands. And that saves us time and also saves us from making mistakes. And then on board, we actually will have an automated scheduling system where we've uploaded all the things we want the rover to do today, and all the constraints on those, like this image has to be taken between this time, and this activity cannot happen in parallel with that activity. All of those constraints are applied to the observations and activities, and the rover will figure out the best order to do them in, and then update its onboard schedule throughout the day, because sometimes things take longer or shorter than expected, and sometimes the drive, for example, might go faster than anticipated, and then you got more time to do other science observations. So the onboard scheduling will be a new thing for 2020, and that will allow us to be more productive. And then finally, the aspect that I'm most closely involved with is the intelligent targeting system, where the rover is able to analyze images on board, identify priority science targets for its instruments, and then point the instruments at them.
And then will the final yay or nay in terms of, well, whether it's imaging or breakdown, will that come from a human command?
So actually, when we're doing autonomous targeting, the decision about which modes to use will have been made before we know what the target is, but the rover will pick the target and then not ask for confirmation from Earth. Immediately after selecting the targets, point SuperCam and make measurements. And that's the Aegis autonomous targeting system that we have used already on MSL, but we'll use an upgraded version on 2020.
Okay, so I think we've covered 2020 very well, given the students a lot to understand in terms of the instrument suite and the science that it's going to be able to carry out. Of course, the driving questions for Martian science for the last few decades have been to, look for life, follow the water, understand the history of Mars. Are there specific driving questions that are unique to 2020, or is it again contributing to this long-standing major questions about the planet?
Yeah, so 2020 is continuing in that trajectory, but now we're at the point where a lot of our questions require the kinds of answers that we can't get in situ. As good as the instruments have become on the rover, they will never be as good as all of the laboratories of the Earth combined. And so the next step is to bring back samples to the terrestrial laboratories. And so 2020 will be the beginning of that process, where in addition to making in situ measurements with SuperCam and Sherlock and Pixel and the other instruments, we will also drill sample cores and seal them up in tubes for eventual return to Earth. And that will influence very much how we do our exploration, because in addition to understanding the modern environment and exploring the geology and the potential past habitability of this place, and of course our other objective of preparing for human exploration with the ISRU experiment, we have this major goal of collecting samples.
So honestly, Raymond, I have to say, I don't really know what you do on a daily basis. Like, you go into JPL, and I imagine you obviously do something, and then you go home. I know it varies drastically between when you're in operations versus when you're not, but what does a typical day look like for you during rover operations?
Yeah, so I do right now operations maybe as much as a quarter of the time. And then other times I'm working in research, and other times I'm working in mission development and this science team training for 2020. When it's operations, you show up to the lab, or some of the science team dials in remotely because we have people scattered all over the world. In my case, I have the good fortune to work actually at JPL, and we have a facility there called the Mission Support Area, where everybody who's working on analyzing the downlink data and telemetry from the rover and preparing the next set of activities and commands that we bundle into a plan and send to Mars. These people work in the MSA. And you've got a room full of people with computers and all the documentation they need to plan these things out. They're on a long series of teleconferences with people at the remote instrument operations facilities in Spain and in Moscow and in Toulouse and elsewhere around the United States and in Canada, I should mention. And we step through understanding what the state of the vehicle is, understanding what happened yesterday and how our investigations and observations turned out, looking at the strategic context of the mission, where are we and what are we intending to do, deciding what we will do today with what's in front of us and what we see and what our goals are, planning out the details of those activities and the observations, checking that everything makes sense, that everything is safe, that it'll achieve our goals, and then preparing the commands, doing final checks and modeling, and then uploading that to the rover. And that's sort of a typical planning day for a Mars mission.
And then you come in the next day and see what happened, right?
Exactly. Yeah.
Yeah, well, and I can't, suggest enough, if anyone who's interested in planetary science or engineering has an opportunity to work on an analog mission, to do so, because what Raymond just described, in a sense, I've been around as well, not in the same capacity, but um, the training that happens on Earth with pretend rovers or sometimes rovers that are just in a desert next door, um, is incredibly valuable for learning how to do work on rovers that are half an astronomical unit away.
Yeah, and I would agree that analog training and mission simulations are a very valuable way of getting experience if you want to get into this kind of line of work. But even here on the real mission, like that's how we're training the science team, is with analog operations, because this is a really good way to get practice before the vehicle is actually on the surface of Mars.
Yeah, so that leads into kind of what I want to wrap up with, but you're from Sudbury originally. You did your undergraduate here in Ottawa, your MSc at the Royal Military College, correct?
That's right.
Yeah, and your PhD at Western, and was that in mechanical engineering or electrical?
Yeah, it was. I was co-supervised in electrical and computer engineering and planetary geology.
So how did you end up helping to drive around a rover on Mars, and what tips might you give to someone who's looking to follow in your footsteps?
Well, it's absolutely, for everyone, it will be the case of being in the right place at the right time with the right skills and experience, which means it's a mix of planning and skill and good luck. And also of taking initiative. When the opportunity comes, take it. So in my case, I came to do this doctorate at Western jointly in engineering and in planetary science because it seemed interesting, because the opportunity was there, and because it seemed like a thing that would help prepare me to someday work on a planetary mission. And I was working on the analog missions that Western was running at that time in 2010, 2011. And on that, I met a postdoc who was at Western at the time, and who was preparing a proposal to become what's called a participating scientist in Mars Science Lab. And this was before the rover even launched. They were calling for additional scientists to join the mission. And he thought he had a productive, cool idea of science that he could do with that rover. And so he put in a proposal, and it involved imaging of clouds. Now, my PhD was supposed to be about automated interpretation of images of rocks. But this proposal from this postdoc, this was Dr. John Moores, who's now at York University. Dr. Moore's proposal involved analyzing images of clouds and automatically extracting the wind vector from sequences of images of moving clouds. And, he saw me working on the analog missions, saw that my specialty was automated image interpretation, and asked whether I could do a cloud thing. And of course, my PhD was supposed to be about rocks, but if someone offers you a potential ticket to a Mars mission, maybe you're willing to also do a cloud algorithm besides your rock algorithm. And so that's what I did. And I joined his proposal as grad student number 1. And eventually that proposal was selected, and that was my ticket to working on the mission, because then I had to deliver an algorithm to process his data. But it also meant that I got to work in choosing how we collected those cloud images, and then in general, how we do science observations on the surface, because everybody on the science team contributes to that planning. And so I learned about rover operations and I should say mission science. And that was a good step into joining JPL as an employee later.
Yeah, it's amazing how much your story is similar to mine in a completely different world. Mine's in the policy world, but I always tell students the same thing: a mixture of hard work and good luck. If you work hard, you put yourself in a position where when an amazing opportunity comes up, you can just say yes and do it. And that's, I don't think we're alone in taking advantage of those good breaks that come our way, as long as
Yeah.
we've done the work ahead of time.
Yeah, what I like to tell people is that life is the vector sum of what you do and what the world does to you.
Mm. Sounds very Spock-like.
Yeah, I think that's an analogy that works well in engineering school. I think, the point overall is just that you're going to have to work with what you're given, but you're also going to have to work.
Yeah, that's exactly it. Okay, last but not least, this is not engineering. Well, maybe it's engineering related. The students in a couple assignments this year have to do some work with some famous space movies. I've talked to all my guests about space movies in one way, shape, or form, but I want to ask you, what is the best Star Trek movie and why?
Oh, interesting. I got to say that I have usually preferred Star Trek on the small screen.
Yeah.
I think I usually prefer the TV episodes to the movies. I think that my top three are, in order of production, Star Trek: The Motion Picture, Star Trek II: The Wrath of Khan, and Star Trek IV: The Voyage Home. Voyage Home is fun, and it does comedy well, which Star Trek sometimes does. Wrath of Khan is a very good drama. And Motion Picture, for all of its, I think some of the seams don't fit together quite right, but the story is probably the most engaging and thought-provoking.
Yeah, and that I agree. No one likes the motion picture, but I love the motion picture. It's a bit slow, but it reminds me of an original series episode. Of course, there was one very similar, but yeah, I thoroughly enjoy the motion picture and don't feel it gets enough love.
It would seem our friendship messages have been received and understood, Mr. Spock.
I would say that was a logical assumption, Captain.
Okay.
So that's all the questions I've got for you, Raymond. Thank you so much for doing this. I know you're busy with essentially 2 rover missions overlapping, as well as all of your research and personal life. So thank you so much for doing this, and hopefully we'll have you on again next year.
Yeah, my pleasure, and good luck to all the students in your class. I hope you're learning a whole lot about how this space endeavor works, and that you really find it interesting and something maybe that you're willing to chase in your career.